Welcome everyone to today's session on the topic of recycled plastics and electronics, when we'll discuss challenges as well as opportunities. But first, we would like to introduce you to the agenda that we have for today. So in order to substantiate the importance of the topic, we will first provide a glance on the global situation of e-waste with the focus of plastics. And then we are going to explore the specific barriers which are currently impeding and hindering the uptake and application of recycled plastics in products, which are actually as complex as electronics. And followingly, we would like to provide insights into the technical and systemic opportunities and solutions which are already out there and which are already on the horizon to increase the uptake of recycled plastics and electronics. And finally, before we open the floor for any questions, we will give you an outlook on what the future holds. But at this point, we would already start with a short disclaimer, because during today's session, we will focus on consumer electronics, so not particularly on the microelectronic scale, but more on the product scale itself. So now we would like to go to the background in order to set the scene. So as all of you certainly know, today we're experiencing an increasing digitalization of the social and economic life, and electronic devices have become an integral part of our lives. So with the still dominant take, make, dispose lifestyle across the globe, we can say that today e-waste is the fastest growing waste stream on a global scale. And on the next slide, I would like to highlight that in 2019, the world generated more than 50 million tons of e-waste. And if you compare this to the amount that is of material that is contained in Eiffel Towers, this would be 4,500 Eiffel Towers. So quite an immense amount. And it is even expected to grow to 74.4 million tons in 2030. So this would almost be a doubling in only 16 years. However, at the same time, globally, we have a recycling rate as low as 17.4% when it comes to electronics. So this means that only 1/6 of the entire volume of which is collected actually ends up in recycling facilities. And in Europe, we have a recycling rate of 42.5% of e-waste being documented. And what is certainly also alarming is that only 2% of today's plastic recyclates are already applied in new electronics. So this would mean that 80,000 tons of recycled plastics are then actually applied in new electronic products. The EU has also set an ambitious goal to actually achieve 10 million tons of recycled plastics to have them already applied into new products by 2025. This would mean that we have to actually double the use compared to almost 4 million tons in 2016. So we already see that it's going to be quite challenging. However, I would like to note that recycling is not the only solution to a circular economy, but instead, in order to increase circularity, we need to actually rethink our way of consumption towards sufficiency and sustainability. And we will also need to reduce the amount of products reaching end of life and implement repair and reuse as much as possible. But after extending lifetime and introducing all other so-called R strategies, recycling also should not get out of focus, because eventually all products will become end of life at some point, and then recycling can ensure that the materials are kept in the loop. And therefore, within this webinar, we would like to focus on the recycling aspect. So while the economic driver of e-waste recycling are certainly metals contained in the products, plastics does make up quite a share of the total fraction. So depending on different products, approximately 19% of the material contained in electronics is actually plastics. And on the right-hand side, you can see that plastic is not always simply plastic, but there are several different types of polymers which are contained in electronics. So you can see that the composition of the plastic fraction from an e-waste after shredding and sorting consists of ABS, but also polypropylene, polystyrene, PC, PCABS. So many different polymers, and also a certain share of the fraction consists of plastics which contains brominated flame retardants, which are actually impeding also the recycling rate, but we will talk about this in just a minute. And currently we are facing several challenges. So plastic recycling remains challenging, but we already have a recycling rate of approximately, or an average recycling yield of approximately 60%. But the sorting of these plastics is actually becoming increasingly complex because of the wide variety of existing types of plastics that are used and applied in the different incompatible. So also when it comes about virgin plastics, which is used in electronics, you call them engineered plastics. So they are used for very specific and demanding applications in order to meet a complex set of requirements and properties. And in order to fulfill these requirements, a large variety of different thermoplastics are being used, and also a broad variety of additives, and such as flame retardants, pigments, plasticizers, stabilizers are often added before processing. So they are used to change the material properties, such as the color, the melting point, the flammability, but also the density. And as a consequence, the polymer composition is actually super complex, and this impedes mechanical recycling rates. The common polymers which are currently targeted in the mechanical recycling processes of e-waste are actually ABS, HIPS, PC, PCABS, PP, and PE. But we will talk about further polymers which will hopefully be able to recycle in the future. But now Ronja is going to introduce several challenges that we are facing in e-waste recycling.
Thank you. Yeah, and before I actually talk about the challenges, I wanted to once depict a little bit on what's actually already possible, because in the police project that was finished 2 years ago, we did some great achievements on like using recyclates in electronics products. And you can see here that there are a lot of plastics already available on the market, recycled plastics, and also for a broad range of applications, you can already use them. Whereas for very specific applications, there are different impediments, which could sometimes be more on the design side, such as using specific colors or requiring a very constant color range, for example. But then, of course, there's also legal restrictions, which may lead to not being able to apply recycled materials. And this is specifically true for medical applications, for food contact, and everything that's related to flame retardant. And that's what we want to focus on today a little bit more. But I also, now I have to, very quickly, to show you a little bit, because often what we hear is, and what we also see here is a little bit like it's mainly black that you can do recycle. I brought you some samples from the previous project where you can see that, for example, here we have a recycled PC in a nice blue, and it's transparent. And what you could see on the chart before too is that, for example, one possibilities of applying recycled materials is because, of course, the quality of the material may be a little bit more inconsistent, or also it may be a little bit less reliable in the appearance, for example, than a engineered plastic. One possibility is to use textured surfaces, and maybe, I don't know how about the light, but in some of the samples you can actually see that. Before it worked better, sorry, that just by applying a textured surface rather than trying to do a high gloss, it's actually way easier to apply the recycled materials. And this is, just guidelines and rules that you will have to learn and know, and maybe also increase your experience about. So exactly, but as shown here, I think there are already a lot of possibilities available, whereas for the cases where we look into, we know that currently there is mainly no material available, and also regulations are often very strong. So to give you an example, for food contact, for example, we are working together with a company that produces a kitchen machine, and there we have the traceability and the legal restrictions, and then of course they also have to fulfill very strict technical requirements, so they have to be steam tolerant for long time usage. And for the flame retarded applications, which you know all from monitors, basically nearly every plastic that is used in offices needs to be flame retarded. There is currently no product on the market that is suited for the compounding. Also, then we again have the legal restrictions that they do not easily obtain the certification. On the other hand, for example, the current way of doing those flame retardants, which used to be bromides, which is now not allowed anymore, but also can be by adding other additives, may also impede the recyclability of the product. So here, for example, we have the problem that even if we apply, if we use recycled content, then we will, by adding the additives, we will actually take out the materials kind of from the circle, because afterwards it's often not being able to be recycled anymore. And so we have the very specific challenges. For example, chemical resistancy. Here it's mainly, for example, we're dealing in one of our projects with like PP, which is already available, but the mass availability is not there. And then again, products that are being exposed to chemicals for a long time may, in the end, not be recyclable anymore, because they just erode, kind of. And the electronic static discharge is a very specific problem. This is we'll talk about it a little bit later, because there you add basically additives that will then allow the plastics to transition electricity, and there is just currently no availability. So we have in various sectors, we have those restrictions, but also along the value creation line of producing a product from scratch, we also see that every specific stakeholder in that value chain actually has a lot of challenges. So we know that the sorting is tricky depending on what's coming in. Users do not necessarily dispose properly of the products. And to just give you one example, left alone the design challenges in the development and design phase, there is just a new need for designers to understand how this anti-recycling functions, and to understand how the recycling processes actually work in order to design for it. And we have to learn along the value chain about different things. So, for example, we need to know what is available on the market from the material perspective. Then also, of course, we need a certainty about the availability of the materials. There are new implications about the geometry that can be realized with recycled plastics. But also when producing, the molds need to be designed a little bit different. They need sometimes higher maintenance because the plastics have a higher abrasion of the tools, and sometimes the circles of tooling need to be adjusted for the speed, but then we are seeing other things that, for example, like in the beginning, many recycled plastics were kind of smelly. So this, for example, has been improved over time very well already. And yeah.
So
Next,
now we're going to we're going to jump into the opportunities. I will start off with the technical opportunities that we are seeing in the industry. So if you could go to the next slide. Thank you. So I'd like to first start off with the current practice of plastic recycling from e-waste, which looks as follows. So the e-waste enters the recycling facility and is they are partly manually dismantled, disassembled, but then shredded. And furthermore, then the shredded e-waste plastics is then, or the plastics fraction is then separated via density separation. So this means that based on the difference in the density of the different polymers, one fraction is actually floating on the surface of the water, while another fraction is then sinking. So in this graph, you can see that, for example, PP and HDPE have a density below 1.0. So consequently, they will be floating in pure water. And if you add salts, you change the density, and then another fraction will be floating. So this way you can separate the different polymers via sink-float separation. And since the sinking fraction contains brominated flame retardants, it is incinerated as required by the REACH regulation. But this also means that any plastics contained in the sinking fraction, which is there due to higher densities, can then be considered lost, or at least only energetically recovered, but not material recovery is taking place. And the floating fraction is then further separated into its different polymers. If you could click once. Yeah, thank you. So for example, with near-infrared separation or electrostatic separation, the different polymers are then separated. But it has to be noted that with near-infrared, the black fraction is currently lost. So the near-infrared cannot detect the black polymers. So since the WEEE plastics fraction contains approximately 40% of dark or black plastics. This means that actually this entire fraction is lost if near infrared is the technology which is chosen. And the reason for this limit is that black and dark plastics contain carbon black, and which absorbs much of the proportion of near infrared, and consequently it cannot be recognized. But on the next slide, you will see that beyond common commercial process sequences, there are several technologies on the horizon and are partly already available, which can help in increasing the share of plastic recycling. So for mechanical recycling, it can I would like to just mention that there are several sorting technologies under development, which we expect to support the increase of recycling rate. So they are, for example, partly able to detect the black fraction, but also to directly detect the brominated flame retardant fraction, which can then be separated already initially. So for example, there are optical spectral technologies such as mid-infrared and Raman spectroscopy, which can provide a more detailed information about the polymer which is being detected, and also detect partly the black and the brominated flame retardants containing fraction. And then there is also the possibility to have the atomic spectral technologies support in sorting the different polymers. So there is, for example, laser-induced breakdown spectroscopy on the horizon, but also X-ray fluorescence, so XRF spectral technology, which can remove brominated and chlorinated flame retardants. And in what also holds the future is actually a combination of those spectroscopical sorting technologies in combination with machine learning to even increase the efficiency. But beyond that, there is also beyond mechanical, there is also the solvent-based recycling technology, which is a promising technology to remove impurities from the e-waste plastic stream and sort the different polymer types. So it is suitable to deal with the sinking fraction, which is currently incinerated because it can remove the flame retardants, but it can also remove any other color pigments or other contamination. And here you can see the process of the Creasolve process, which was developed by Fraunhofer IVV. So it functions as follows. The waste, so the shredded plastics fraction, enters the solution and is then dissolved, but only the target polymer is dissolved. So for example, ABS, and then after various purification steps, the polymer is cleaned, consequently precipitated and dried, and then you have quite a virgin-like quality of polymer, which you can use again for production. And besides mechanical, here you can see that the solvent-based recycling can actually deal with the sinking fraction, as I mentioned. So this would mean that for the floating fraction, you would have, for example, in a future scenario, more sorting technologies, such as mid-infrared, Raman, XRF, as I mentioned. And then for the sinking fraction, you could also make use of it instead of incinerating the entire fraction by, for example, applying solvent-based recycling. But on the next slide, I would also like to mention that there is also chemical recycling on the horizon, which decomposes the polymer into its monomers. And so we have 3 different technologies that I would like to mention. So there is depolymerization, which actually decomposes the polymer into monomers, pyrolysis, which has hydrocarbons as an output, and gasification, which produces syngas. And for pyrolysis, I'd like to mention that there is also already a technological readiness level for packaging of TRL8, so this is quite high. But for the WEEE plastic stream, it's still relatively low, so it is upcoming. But the future holds still what is about to come and how effective it can manage the recycling of plastics. And here on this slide, you can see the different recycling routes. So on the left-hand side in this model, you see the different cycles. So mechanical recycling actually closes the loop with a quite relatively low process energy, and then solvent-based recycling and chemical recycling can be complementary to actually deal with those fractions that mechanical recycling cannot deal with. And regarding further opportunities on how to increase the recycling, on the next slide, I would like to mention that there is this innovative solution of clustering products for separate recycling. So when looking at the composition of here, for example, 3 different small household appliances, which are actually collected in one stream, you can see that, for example, vacuum cleaners, coffee machines, and printers already exhibit quite a different composition of polymers. And in the police project, which Ronja already mentioned, we conducted clustering experiments to see whether better recycling rates and higher quality grades of recycled polymers can be achieved by recycling those products in a separate stream. And it was found that by applying an adequate clustering strategy, for example, an estimated 500,000 tons of e-waste plastics could be recuperated on an annual basis in the European Union. So this would equate to roughly 16% of the total e-waste stream at collection. And on the next slide, within the police project, one strategy was already developed based on the demonstrator cases on how to best cluster the different product families. And on the left, you can see the WEEE categories, which are proposed by the WEEE directive and which are expected to be collected together. And it was, for example, proposed or found within the police project that fridges and freezers, when treated in a cluster, can generate quite good results for high impact polystyrene, or coffee makers, when treated separately, can generate good quality recyclates of PCABS and PP, for example. And last but not least, another possibility to increase the recycling rate is the combination of those different technologies. So in the course of the follow-up project of the police project, which is the Increase project, we are currently combining different recycling technologies, as you can see here, in a complementary way in order to maximize the overall yield and provide tailored solutions for the different business cases that we have and that we are tackling within the project. But each technology, of course, has their pros and cons, which need to be also taken into account. And I would like to stress that currently there is a lack of data on the environmental impact of the different processes regarding the different specific polymers. So this is something, for example, that we are looking at within the Increase project, and where we hope to find some promising results. We cannot yet hear you.
Sorry, exactly, because overall the objective, of course, is to find a more sustainable solution than we're currently having with the waste. And this is, of course, once the resource consumption, but then, of course, also the energy efficiency of the processes. And currently, the different recycling technologies have very different energy consumptions and efficiency rates, which, of course, is also due to the fact that they have a very different market readiness. But then again, we also should not forget that some of the processes and of the materials themselves need different energies. And there's very little data currently available on this, but what you can see here is that the comparison of HDPE and PET already shows that the HDPE itself uses less process energy. And this is something that we should bear in mind, because what we currently see a lot is that companies replace their current material to, for example, recycled PET, which of course then is good for claiming recyclability and the recycled content, but it's cannibalizing kind of the streams. For example, the PET is high quality food contact approved material, which then should not end up as a coat hanger, for example, unless it cannot be food contact anymore. And then also, if it uses more process energy, then it's doubtable that it's the right application. So keeping that in mind, what can we actually do in order to increase recycling rates? From a design perspective, we have a little bit the hand and egg problem. So currently we have a lot of products that are difficult to recycle because they already have not been designed for recycling, and the recyclers have to deal with it. And then we have to start designing so that products can be easily recycled. And then, of course, we should also start designing so that we can apply recycled content. And one very general approach to this is to, first of all, when you start a project, consider what is already available in plastics types in recycled content quality, because that, of course, if you take that as a brief for your product directly, then you will design accordingly. Also to check for overspecification. I can explain that a little bit later, but that a lot of producers actually use general specifications that they know from other products, and they are all often overspecified. So they need to reach technical requirements that are actually not necessary, but therefore the availability of alternative materials shrinks, of course. And then one very simple approach also is to make changes when new tooling is needed. We just came back from a customer project where they had fiber enforced housing, and we asked why, because it didn't seem necessary, and they said like, yeah, originally the tool was already there, so we needed to use the tool and we enforced it with fibers because otherwise it wouldn't be stable. But then when the tool changed, the fibers just stood in the specification rather than redesigning the product accordingly and using non-fiber enforced material, which then of course could be more easily recycled. Very important is to separate hazardous materials and to avoid them, of course, in the first place. But if you need to use them, then use them in separate parts that are easily disassembly, so that in the recycling process they can be taken apart before everything gets shred, and they are not in there. Same as for liquids that need to be in the product or in the process. They have to have valves or drains so that you can remove the liquids exactly. With electronics, for example, you should try to avoid to put magnetic parts in the PCB, because then the PCBs with all the valuable components will end up in the ferrous separation. That's something really we have to understand how the current recycling processes work in order to understand where things will end up and then design accordingly. Exactly. Then for the plastics itself, we should try to avoid coatings and lacquers, all kind of secondary treatment, chromes, and so on, and rather try to play with the surface of the plastics directly and use it as a design. We can see here in this sample that they, rather than putting a sticker or something, they just molded in the label of the company so that that the part is still a monomaterial, which is already also, of course, then a directive, like use monomaterials, try to separate the materials, do not use materials and combine them, especially that can be recycled and those who can't be recycled. No thermoplastics, because there are currently no recycling technologies, and especially and every time that you have to use it for requirements or technical critical requirements, then try to not mix them. And something else that we have to learn, I think, is about the molding and the geometry. As I mentioned before, recyclates may not have the very same performance as virgin materials. So we have to learn how to build the tools, and I think it's actually something that we learned when we learned about using plastics in the first place, probably too. One thing that is already known, that is, we need a little bit more of venting ports, because often the off-gazing in the tooling is happening more just. And of course, also like very complex tight geometries where we have long flow path, where we have tight and narrow geometries in the tool. Those should be avoided too. So just changing the geometry. But something that we also learned, and that the partners of ours also learned, is that technically, once you understand how it's working, it's just the very same design process then again, because you just have new requirements that we as designers and engineers have to deal with anyways. So, and then other things are like in time-wise playing for us. For example, as you can see here, we see two products, one a little bit more radical using recyclates. They do not hide it anymore, but they just play with it. And every single product looks a little bit different. But this is now just the product appearance, and it's like the brand itself. And a little bit less radical approach to it is when Sonos just changed their requirement from a very pure white to a little bit softer, whitish or grayish white, they could actually increase the recycled content rate by 40%. And they decided to do it because they said, like, technically now, if a consumer will put like 2 of our products from 2 different generations very next to each other, then they will see the difference. But otherwise, no one will really see that it's not this pure white anymore. So a key learning is definitely that we have to address the entire value chain and also have a company-wide understanding and commitment to the idea, because otherwise in many projects that I talk to, it's often the marketing that then will say like, no, but customer will not expect it. And what we're currently also researching is how much is assumptions in there, because we see that there are lots of assumptions which may not be true anymore. Then, as I already mentioned, the design for recycling becomes quite similar to the current flow once we know of the hurdles. So if you inform yourself, or the designers have the opportunity to inform themselves, then they can just take it in. Of course, then we have to take a little bit more time, which then is, of course, development time and budget. That's for sure. But when we work together throughout the production and the engineering, for example, we quickly learn on for example, what's possible with the tooling, and then can implement it easily. And a different learning is also that by closing loops, more on the economic side, and really closing the loop for there's an increase of quality and availability, because of course, like if you send it anywhere and then you shred and mix everything, then it's way harder to get a specific color quality out of there rather than when you try to collect it before and sort it beforehand. On the other hand, we also see like more over the entire supply chain that there's financial incentives that can play for the recyclability and recycling increase. This is, of course, tax benefits and refunds that we already see raising in some of the European countries. But also internally, there can be hurdles that can, for example, be overcome by allocating CO2 budgets to the specific departments, and then they start trading internally. And this will avoid, because otherwise one department may try to shrink the CO2 budget, but it will increase somewhere else. What we see often happening with little interventions. And so with this, we can see that there is more life cycle oriented thinking, which then supports the entire objective. And of course, currently we still see that we need adaptations and regulations because we have just conflicting targets. And I was amazed to yesterday only learn that even a shower head in Germany needs to have food contact approval, because technically it's drinking water flowing from it. And so it needs to be like, they can't apply recycled content for the nozzles because then it could be contaminated. But yeah, there are opportunities. And as I already mentioned, the overspecification is something that we see a lot. And one of our current project partners is producing these ESD discharge pallets. And there, for example, there is just no real reliable data available on how much of the carbon black, there's carbon black mixed in the plastics in order to make it discharge. But we see that it's way too much. So we are testing currently on how much that we need actually, and how the mixture can be done better, so that they do not put in too much of the material that will then also impede the recyclability. And here again, it's a big product using a lot of material. And here the closed loop system with jumping on the already existing take back system for pallets, for example, would be one opportunity in really obtaining the pure material back and then recycling it directly. And we also saw from different projects that some of the companies really said that for them, now they have a expertise in a new market segment, and they are pioneering in a specific area, which then makes them claim new market segments. And altogether, I took that example, which is not from our partners, but I think what we still in electronics specifically have to understand that we really have to find holistic solutions considering the entire circular economy and not only the recycling. And by closing the loop and providing like closed systems, business models too, the manufacturers can actually keep the control over which flow and which loop in the circular economy is addressed. Because obviously for most of the electronics parts or products in the market, refurbishment, reuse is the first option, and only afterwards the recycling is an option. But here again, we see, for example, we know that suppliers of washing machines, let's say, they have very specific requirements, and then they want really this specific material back, and they say like this white with this amount of chalk we need, and so on and so on. And of course, for a compounder, this is very tricky to get from the recycled market. So if they take back their material and they establish smaller recycling plants on their plants, where we already see technologies rising, allowing for that, then they can just shred their materials and have it in the right quality back.
So now, finally, a quick glance into the future. So with the speedy technological advancement and also continuous change, of course, as we see it in fashion with products, we can observe this a similar trend in the plastic fraction of electronics. So here you can see that, for example, in 2012, HIPS and ABS made up more than 50% of the plastics fraction, while in 2020 there are also PC, ABS, PP, which are actually making up quite a share of the plastic fraction in the e-waste. And this also, of course, means that recyclers need to adapt their processes, which eventually means that this also influences, of course, the availability of recyclates in the market for application in new products. And technology-wise, I've already mentioned that there are several emerging technologies which we can see already on the horizon when it comes to recycling of e-waste plastic. And this specific future scenario was developed in the Non-Tox project, which was a Horizon 2020 project. And you can see that the processes that are marked in green are actually the ones that are upcoming, and that will allow for increasing the share of recycling. So with further optical and density sorting and solvent-based recycling, and also chemical recycling processes such as pyrolysis, we hope that more recyclates will be available and more recycling will be done.
So to conclude quickly, currently we have a kind of siloed actions that we see that are still, we're trying to achieve the same things. We have regulations that try to prohibit, we have regulations and directives that try to incentivize. We have a demand for recyclates at the market, but then maybe a little bit too less willingness to also adapt to what is recycled content. And for us, what we're also trying to achieve with our project is to really align the actions. And I think there are top-down decisions that need to be taken, and of course also the impeding regulations that maybe conflict with each other that needs to be solved on a EU level at last. But then there is also, we have to start thinking differently and just applying it. And I think every company should start by testing and gaining experiences. And one approach is definitely to understand that that secondary raw material perspective that Theresa already said, like thinking of what will be available and then using that. We're also working together with a partner that will provide better prognosis on the material availability and to make it more plannable. And then then this like implementation of first ideas will just increase the knowledge. And then I can't really see all questions, but I already saw one about the financial aspect of it. Of course, currently it's very hard for recyclers to work on an economic rationale, because they get this like very mixed materials that are glued, screwed, welded together, and then we ask them to just provide us pure materials back. So as mentioned, when there are more materials, like the technology is improving, but also the design needs to improve in order to make the process economically available.